Hello everyone. Today my topic is morpheme enhanced spectral word meetings. The first, we need to introduce some elements in title. The first is that what is word embedding? The definition is that word embedding is to represent words into low-dimensional vectors, like the following examples: the apple and the tiger. There are some very famous related works like the Sable, seke2017, One Hot Reputation, and Globe Vectors. The second is that what is the morpheme? Morpheme is the smallest unit of a word which still has some meanings, like the English prefix, suffix, root, and Chinese characters. Um, there are still have some weaknesses of this related work. For examples, with regard to the continuous back of words, this these models use context word to predict tagged words. The first layer is input layers. The second layer is hidden layers. The output layer is tagged words. As we can say, this word can only capture some word level semantic informations and ignore the meaningful information of words' internal structures. For examples, in English, the prefix pre has the meanings of before. The prefix anthropo has the meanings of man and human, like the word anthropologist. Um, the suffix er have the meanings of man and human, like singer. In Chinese, characters feng have the meanings of wind and sing. Character guang have the meanings of light and sea. However, in traditional word embedding models, these their meaningful internal semantic informations um, is, is ignored. So our work is to now target of our work is to improve the quality of word embeddings by incorporating the morphologic information by using spectral method. The methodology of our work is divided into four step. The first step is that we need to build the word information matrix W. The second step is to build the context information matrix C. The third step is to build the morphologic information matrix M. The last step is to do CCA on these matrices. Firstly, we need to introduce construction of word information matrices. Like the picture shows, the first um, each row means the word in the corpus, and the column means the vocabularies. First, we need to choose the top M words as the vocabularies according to the word frequency. If WI um, isn't in the vocabulary, then the corresponding then the positions of NAR will be set as 1. Um, if the WI in the vocabulary, so the corresponding position will be set as 1, which means that each row in this matrix is one hot vectors. Next, we will introduce the context information matrix. Like the picture shows that the context information matrix is divided into two parts, including the left context matrix and the right context matrix. In these pictures, we assume that the context window size is 1, which means that if we, for WI, we will only consider the WI minus 1 and WI plus 1. If wi minus 1 is equal to the vj, then the corresponding position in left context matrix will be set as 1. If wi plus 1 is equal to vj, then the corresponding position in the right context matrix will be set as 1. Um, then we'll introduce the morphologic information matrices. In this paper, the morpheme is divided into three parts, including the prefix, suffix, and root. Um, Thus, the morphological information matrix is also divided into three parts, including the prefix matrix and suffix matrix and root matrix. If wi has the prefix, then the corresponding position in the prefix matrix will be set as 1. If wi have suffix sj, then the corresponding position in the um, suffix matrix will be set as 1. The root matrix can be constructed in the same way. Then we will concatenate matrix from the from the column directions, and next we will do CCA on these matrices. The first solution is named MOMC. The basic idea of these models is that we view the morphological information as an unit feature. We will expand the matrices W and C. Um, the W new is constructed like the following equations. We will concatenate W and morpheme information matrix M from the row column directions. The the C new is constructed like the um, following equations. The first, we will concatenate the left context information matrix and the morpheme information matrix, and next we will concatenate the right context information matrix and the morpheme information matrix. Then we will use the results to construct C new. Then we will do CCA on W new and C new. The second solution is named MC. The basic idea of these models is that we view morphologic information as a global features, which means the morphologic information is viewed as a kind of context information. So we expand the matrix W and C like the following equation shows. Uh, W new is equal to W, and C new is constructed like the equation shows. We will concatenate C and morpheme information matrix M. Then we will do CCA on the W new and C new. We will use corresponding projections of these matrices as word embeddings. Then we will introduce experiments. The first experiment is named word similarities. This experiment is used to evaluate the ability of word embeddings to capture the semantic informations. The dataset of this experiment is divided into three columns. The first column is the word 1. The second column is word 2. The third column is human scores, um, which indicate um, the similarity between these words according to the human judgment. The first step is that we need to calculate the cosine distance between W1 and W2. Then we will measure the correlations between the distance and the human scores. The larger correlations means the better performance. The second experiment is sentiment classification. The first step is that we need to average the word vectors in a sentence. This, the next step is we can use some best classifiers to do text classification based on the average of word vectors. The result of the experiments is like the following tables. As we can see, now models MO, MC, and MC get the best performance on the most of the dataset. Then we test now models on uh, morpheme-rich languages. We use the German corpus to train a part of German word meanings and the test them on by using the word similarities. Like the tab shows, now models MC gets the best performance on all datasets and um, MC performance much better than now the basic models of our models named one-step CCA. The morphologic similarity of all embeddings is illustrated in these pictures. As we can see, in the vector space of our models, words with similar morphemes will group together in vector space, which uh, demonstrate the effectiveness of our models in dealing with some morpheme-rich languages. These pictures illustrate some semantic structures of word meanings. In these pictures, um, words with similar semantic similarity with similar semantic meanings will group together in vector space, which means now models can capture semantic informations